Today, we will be talking to you guys about waves and wave interference. Many things in today's world can be considered to move in waves. A good example of this is the guitar you see on the screen right now. Each time the string is plucked, waves are interacting with one another, causing sounds that you would be hearing if you weren't hearing my voice right now. Every time a guitar string is plucked, it results in the creation of waves. These waves can interact in both constructive and destructive ways. The result of these interferences creates the sound that we hear.
Classical wave. Waves in a physical sense, like waves that you may find in the ocean, have recognizable characteristics like height, and they have peaks and troughs which define them. Quantum waves lose some of this as they are waves of probability and position, but both are held together by a set of mathematical equations which govern them. These mathematical equations use parameters such as frequency and intensity. We can carry information that we can take from the classical sense and use that in our understanding of the quantum waves to help better understand the quantum waves and their behavior, as far as characteristic parameters such as frequency and intensity.
Single wave source and diffraction. When two waves are in phase, the path difference is equal to an integral number of wavelengths. The summed amplitude, and therefore the summed intensity, is a maximum. And when they are in antiphase, the path difference is equal to half a wavelength, and 1.5 wavelengths, or etc. Then two waves cancel the sum and intensity is zero. This effect is known as interference. The interference fringe maximum occurs at differentiating angles. When this experiment is performed, a spotting pattern of light is observed at the bottom of the tub. That is to relate to whether or not the waves are in phase or interfering constructively, or out of phase interfering destructively. As you can see in the experiment, the ping pong ball is being used to propagate the waves, which we are replicating in a tub of water. A plate is used as a shield to prove diffraction. You can see the waves in the shadows of the tub on the bottom.
Two wave source interference. When waves are being propagated from two sources, the resulting waves can interfere with each other. This is very similar to the wave interference experience with diffraction, but instead of one wave source interfering with itself, two wave sources are interfering with each other. In the case of the water bath, two ping pong balls are being used to create the waves. When the waves from both ping pong balls begin to interact, the pattern that is seen in the shadow of the waves changes. It starts as the familiar circle shape, but as the waves continue to interfere with each other, the pattern changes to create almost diamond-like shadows. This new pattern is simply a sum of the two original waves that are interfering. This example can be compared to the bonding that occurs in diatomic molecules. When two atoms are close spatially, the wave functions of the electrons begin to interfere in similar ways. In this case, instead of the diamond-shaped pattern being formed, a chemical bond is created instead. The linear combination of atomic orbitals is what takes into account the wave interference of the electron wave functions. While this interference may have different physical meanings than the classical model, we can use the ping pong balls to imagine what is happening when chemical bonds are formed.
Wave interference.